up? Oh, okay. So now recording has been started and I messed up my setting, but all right. Got it. That's let me reset a few things. There we go. All right. So let's get started. As I said, we'll get in slowly, and this will leave the time for the people to still join us. So who am I, and why am I talking to you today? So my name is Romain. I'm French originally. I did my doctorate in Switzerland at ETH Zurich, under the supervision of Professor Thiele, that some of you might know as a pretty known figure within ESWEEK. And during my PhD time, I worked on real-time communication protocols for low-power wireless embedded systems, so more on the networking side of things. And now, since I finished my PhD, I'm not doing a postdoc position still at ETH, but moved into computer networks, so essentially the internet and how the internet is operated today. All that to say that my personal background is strongly focused on networking and protocols in general. And so that being said, before we got into the meat of today's tutorial, I would like to make two slight disclaimers. So the first one is related to what I just said before. I'm a networking specialist. I'm not a machine learning specialist. And the topic of this talk, the meat of it, is not about ML. I will, towards the end of this presentation, talk a bit about my views on replicability challenges in machine learning. Most of the things I'm going to talk about are applicable to machine learning to some extent, but keep in mind that this work was not designed for ML. Now, second disclaimer is that I don't find it very nice to work on a Sunday. To be very frank with you, I agreed to do this presentation a very long time ago, and I actually did not really pay attention to the dates. And I just would like to mention to all of you, PhD student or postdoc that might be watching this presentation, please do not take it as a normal thing to work on weekends. I don't think that's a good habit to have. With that out of the way, what is today's tutorial about, or lectures about? It is about replicability and more generally, how to answer two essentially quite basic questions, but quite difficult, which are how to design experiments, how do you size them, and how do you analyze the data that is coming out of your experiments. As I said, in my talk, there will be a focus on networking. The examples that I'm giving relates more to this, but as I said, can be extended to other contexts as well, as you will see. And we're going to focus on experiments that tend to assess performance. So not initial exploratory experiments, but the type of experiments you do in order to really say, like, my system improves performance by X% compared to the state of the art. So the later stage performance evaluation. And the goal of the approach that I'm going to talk about today, I'm going to present, is really to foster replicability. So what I mean exactly by replicability, I'll get back to this in the beginning of the presentation, because as you will see, the terms can be slightly confusing. Now, this is supposed to be an interactive lecture. I feel like we're going to be a fairly small group today, so it's quite narrow audience. So please take that as an opportunity to interact even more. I would invite you to ask any questions in the Zoom chat. I have it open. I'll try to monitor that from time to time. And there will be a specific time for asking questions during the presentation, or I will prompt for that. And at this point in time, feel free to unmute yourself and ask questions by voice. This will also be more than welcome. So the structure of today's presentation is going to be as follows. There will be two parts. In the first part that I'm already starting now, with a larger part of lecture and then a small hands-on session, about 15 minutes. Then we'll do a break of 15 minutes, and we do a second part with a slightly shorter lecture part, and I won't have time to go too deep, so a very short hands-on session before we can wrap up and have a bit of a discussion about the lecture in general. So that's the plan for today. I suppose there are no questions so far, so let's get started with the first block. So in this first block, I'm going to talk about those three things. I'm going to try to motivate first what replicability is and why it matters. And I'll show some examples of that. Then again, I'm going to argue that in order to address replicability, we need to understand, well, the enemy of replicability, which are the sources of variability, which is going to lead me to talk about this notion of timescales, which are very important for replicability, at least in the networking context. And finally, we're going to end this first block with some basic knowledge that you need to have that relate to statistics in order to do better data analysis and even experiment design so that you can foster replicability. All right, so let's get started with why replicability matters. For that, let me take the following example. Let's say a given team of researchers have designed a low wireless communication protocol they call Banana, and they set up an experiment to validate the claim that they want to make. And so what do? Well, they deploy their system on a testbed. Some of them are available hosted by a research group. They run their algorithm on some benchmark problems that have been, for example, set up by the IoT bench. Then they compare performance to what is currently the state of the art, let's call it Kiwi. And then they run each protocol 10 times. Now, they summarize the results. They want to show this is extremely low power. So one metric of interest is the energy consumption. And they do their experiment and they show in their paper results like this. And next to this, they claim that Banana achieves a 2x improvement over Kiwi. Let's say you look at the plot. Now, let's say that you are reviewing this paper. Okay. Do you think that 10 runs are actually enough to support such a claim that Banana improves 2x, shows a 2x improvement over Kiwi? Now, I would actually like you to answer that question. And for that, we're going to have a bit of a clicker thing. So please open a new browser window and go to slido.com and enter the following number, 123011. And then you will be able to enter your answers. I'm going to start appearing in a second. I should be seeing the number of answers as we go, but last time I tried this, I had a bit of an issue. So the answers are not coming in yet. So please take a minute, think about that. Do you think that 10 runs are enough to support a claim such as 2x improvement over Kiwi? I'll give you a minute to connect to the Slido thingy and give your answer. All right, so only 2-3 answers for now. I would have hoped for a few more, given that we are 16 in the room. But let's get going with that, because the overall distribution of things will probably not change, which is that, I mean, either you're not sure, probably it's not enough, or you're really sure it's not. Okay, so now comes the tricky one. How many runs do you actually think are required to support such a claim? Okay, if you have been designing Banana, how many runs would you have done? And here comes second clicker with some categories. And I'm actually much more interested in that one. So what do you think? 5 to 30, 30 to 50, 50 to 100, more than 100, or you just really have no idea? So let's see, we have 5 answers, and for now, essentially, people says either they don't know, or they think like you should do really a lot, like more than 100 tests. Okay, I'm going to move on for the sake of time, because we are actually, I usually do this tutorial in 3 hours and we have only 2 today. So I'm going to try to be a bit more efficient. My personal answer to that question, the second question I ask, is that we cannot answer it actually. Why cannot we answer it? Because it's not clear what type of performance we're talking about. What does that mean when you say you improve by 2x? Like, what type of metrics are we considering? Well, we know the metrics, the energy consumption, right? But are we talking about the average energy consumption or the worst case, or what is it exactly that we are really interested in quantifying? But let's say we clarify this and we say the median energy consumption shows a 2x improvement. It's already much more clear. We have a better idea about what we are claiming about. And I'm not going to poll you again, but think now that even if we were doing the experiment and we clarify that this we have here the median, we claim that we achieve 2x improvement on the median, would you feel confident that if you would be repeating the experiment, so comparing banana and kiwi again, you would obtain the same graph, right? Regardless of whether it's sufficient or not to say it's 2x improvement. It's not so clear. It's not so clear. It's pretty hard to say because we are not really 100% clear about what same results mean. Like, what does it mean to obtain the same graph? Of course, you expect some variability, but how much is to be expected and how much is too much? Those are very hard questions. Those are generally difficult questions to answer, at least in my opinion. That's what I found in my own research. And that's why this lecture is about. This tutorial is about I'm going to present a rational methodology that allows you to answer those two questions. How many runs would you do? Do you feel confident you would obtain the same result in a rational way? And we have implemented this methodology into a framework that we call TriScale, which I'm here to present today. So, in my intro, I promised that I will clarify what is replicability. So here it comes. Here's an illustration of different dimensions that compose the replicability environment somehow. And it's often shown, and the different terms are classified along two different axes. On the columns, you have the differences between whether you use the same data or you use different data for your experiments. And on the horizontal axis, you have whether you use on the row, sorry, you have whether you use the same analysis and different analysis. I'll give some example of what it means. And replicability is on the top right, and it's at the intersection of using the same analysis, using different data. What does it mean? It means that essentially, you're asking the question, am I able to obtain the same results than the original study if I recollect new data based on the same experimental setup and data analysis pipeline? That's generally what that means. That is replicability. That is what we're going to talk about in this tutorial. Now, you could ask whether this actually matters, right? And most people that care in that topic will obviously say it does, but why does it matter? It matters because essentially, if you think of it, if you're not able to replicate an experiment, then that experiment is not really qualifiable as science because it's just random, like if no one can reproduce your thing. Putting into a picture, this is essentially just like this. It's pretty simple. If you do something once, which is on the right over there, then it's not really good science. If you're able to show the same results multiple times, then it's more sound science or better science, let's say. Now, interestingly, a couple of years back, a journalist surveyed scientists across many different fields and asked whether they thought there were something of a reproducibility crisis in their field. And the results are quite clear. Like, most people do think there is a problem, either a significant or a slight crisis in their own field. The source and the origin of that crisis might have very different sources, and we're not here to cover them all, and we're not here to dissect those results, but essentially there is some kind of a problem and that needs some attention. And you may wonder whether this is particularly a problem for the computer science field, networking or embedded systems more specifically. And well, my answer is clearly yes. And I would like to give one recent example, which is about performance on cloud computing. It was presented at NSDI last year, where researchers essentially asked that question, like, if we take the papers from the literature, are we able to replicate the results? Like, how well does it work? And if I'm showing it today is that it doesn't, right? It doesn't work very well. The variability in the results is extremely poorly documented in many cases. People use in many papers between 3 and 10 runs. So thinking about the original motivation example I had earlier, like many of you said, 10 runs is definitely not enough. We need 100. And here we are talking about a similar context where actually often enough when people do report their numbers, they report very few numbers of runs. And altogether, those are papers that are like extremely well regarded in the field. Like this is the state of the art. Like, and it's not saying the work is bad. It's saying that the work is not necessarily well documented or using arguable experimental practices. And we can do better. And I'm here today to show you some means of how to improve on that. And of course, this is no news, right? And many people have realized for a long time that replicability was a serious issue, that something needed to be done about it. And so you will find in the literature some attempts or initial proposals to address those things. I put 2 here on the slide. You might know them, you might know others, but everything that I found in all CS field that I know so far are mainly guidelines. And the problem with those guidelines is that they lack really concrete answers about those practical questions we were asking before. How many runs? Do you think that, what is your confidence that you could reproduce those results? And it's not about just saying, do more runs that will help you answering how many you should do. So yeah, again, this is what I just said, like how many runs, how many times should you repeat your experiments? It's a question we've started with what statistical method you should actually use in order to synthesize the results so that, well, chances are better that your conclusions are sound and can be replicated in the future. We don't know how to answer those things. We lack this concrete methodology, and TriScale, as I introduced before, is trying to provide that. So that's what replicability is, and that's my arguments to try to convince you that this is a serious problem that matters. Now, interestingly, I think it's important to understand where the variability stems from, like from what is the source of the variability, so that we can actually counteract it and eventually achieve replicability. So let's talk about this for a second. Before we can do that, let's take one step back and realize and think about what is the evaluation process that we do in our experiment. Like, how does it look like? At the basic level, this is what we have. We have a system under tests, which we measure, and we measure it how we put some input X into our system, and we get some output Y. That's like the most basic measurement process you have. Now, in most cases, you don't only put one input to get one output. You do that many times. You want to test multiple settings, so you get vectors of values. And as soon as you get vector of values, in order to report results, you don't gotta put all your individual results into your paper, right? You're gonna synthesize them somehow, taking the mean or other things, right? So we create a second step. Not only we need to measure, but we need to synthesize results. And we have a couple of issues in this process. One of which is that your system and your test might not be deterministic. And if you do wireless communication between 2 nodes, it's a somewhat stochastic process. Like, it's not guaranteed that the communication will succeed between 2 nodes, but it may not. And you can quantify this uncertainty. So because your system and the test might exhibit some non-determinism, then typically, as we've discussed so far, you would repeat your experiment. Like, you have your set of values you want to test, and you do multiple repetitions of that to increase confidence. But that makes the synthesis step even more complex. And something which is extremely acute in embedded systems, is that we test our systems within a certain environment. And if I do wireless communication, well, the RF environment around my system and the tests is the environment. And this is also highly non-deterministic. There are also other sources of non-determinism that pertain to the measurement process itself. For example, the measurement error, and all that adds up. And all that adds up, and in the end, it's a fair question to ask, what is the confidence we actually have, or we can have, in the performance result that we report at the output of our synthesis step? So that's the problem. Now, I highlighted here some high-level ideas of what are the sources of the variability. Now, I found that one interesting way to look at this was not to look at the sources of the variability, but how the variability looks like in the data. Let me show you an example. Let's take the time axis where we're going to do our experiment. Let's say we measure some quantity y here and above me over time. We have, for example, power draw of an embedded system over time. We observe some fluctuation. Fine. This is one run. We do this experiment one time, we obtain one set of value. Now, and typically in our synthesis step, we're going to take the mean of our measurements, and then we're going to get essentially go from power consumption to power draw from energy consumption. And that's that. That's the result we get for one run. Now, if you repeat those runs, most likely the metric value that you've computed here gonna look slightly different. You're gonna have, again, some variability between those things. And that's the usual process, right? You test your system, you compute the metrics based on the run, then you run multiple times, and then you have a second step of synthesis. In this presentation, I will refer to the second step and the second aggregation as a KPI, or key performance indicator, which is a terminology used in neighboring fields. Now, think about this KPI value and think about what if you were to redo this series of run 1 week later, or a month later, or a year later. Very likely, you will not obtain exactly the same KPI value, right? You're going to have some sort of variability. It's going to be slightly different. And this creates a third layer of variability that you can see in the data. And so the conclusion is that in the end, we observe 3 different types of variability. And variability is exhibited along 3 different time scales: during one run, during a set of runs, which we call series, and across series that we repeat over time. And there are a number of questions that we can ask ourselves based on those different time scales. For the run, we can wonder whether we've tested our system for long enough. At the scale of the series, the question we had previously already, are we performing sufficiently many runs? We could also ask yourself, how should I schedule my tests? Should I do them all in the same hour, or spread them across the day, or spread them across the week? Depending on the type of test you're doing, that can have a significant impact on the results. And finally, if you're interested in the replicability of your experiment in the long term, then you should also ask yourself, similar as how many runs, but how many series should you do? And at the end, in the end of the day, I found that those 4 questions are the key question that one needs to answer to design an experiment, to design a performance evaluation experiment. And the goal that I set myself to was to try to find rational answers for those questions. And when I say rational, I mean answers that make statistical sense. So in the introduction, I give you this story example with banana and kiwi, and it's not about saying like, for 2x, you need 100 runs, right? Like we need to be able to justify how many runs, so how we decide on the number of runs we do. That's what I wanted. And I found a way to do that, which I'm going to introduce now. Before we can do that, we need to recap a few basics about statistics. So don't run away just yet. I promise this will not be mathematically hard. And you will realize that there's actually not much reason to be scared about statistics, even though when you talk with people, it's usually like, oh, statistics, I really don't like it. So let me reassure you, we're going to start very slowly. First thing first, what is a statistic? Well, super simple. A statistic is a numerical value that you compute based on a set of other values. That's all it is. Not super scary. Right? Now, slightly more interesting, you need to pay attention to the difference into two very different classes of statistics that are known as descriptive and predictive statistics. The difference is that the descriptive statistics tell you what the data is like, whereas the predictive statistics tells you what the data that you have collected allow you to infer about future data or data that you did not collect yet. And this is quite different. And as you might have guessed, in the context of replicability, we are asking ourselves the question, can this, will I manage to obtain the same results again if I redo the experiment? This is a prediction. This is the type of statistics we are interested in computing. Now, let's take again a sample of data. So we measure something, we have a sample. Okay. Now, typically in this context, people will do an aggregate, a synthesis step, as we discussed before, and for example, compute the mean of the sample. This is perfectly fine. And this is a descriptive statistic, right? We have a numerical value, the mean, which gives us some information about the central tendency of our sample, right? What is the average value that we get in our sample? Now, more interestingly, what we get is that with a set of samples, those samples are actually coming from an underlying distribution of all the possible values that we could have get. And of course, this distribution, we don't know, right? We have no idea a priori what this distribution looks like. This is why we do the experiments to get the samples in the first place. Now, this distribution also has an expected mean, right? And what we try to do, or what we should be trying to do in the data analysis process, is that based on the sample, we try to estimate the distribution mean, or the expected mean of the distribution. And because we are doing a prediction, predictions are always uncertain, right? That we will never be sure 100% about any sort of prediction, otherwise it would not be prediction. So there is some uncertainty, and that uncertainty I represent here with this shaded area on the graph. And so here on the top, on the top and on the bottom, you both have mean. They are both statistics, but they are different classes. At the top, we have an empirical mean, which is the mean of the sample. That's a description. But in the data analysis, in the process of replicability, we are much more interested into the distribution mean, or estimating the distribution mean. And that's going to be a prediction. So predictive statistics. To sum it up, a descriptive statistics tells us something like the sample mean is a number X, whereas the predictive statistic tells us, like, based on the data I have, if one were to redraw a new set of samples, the sample mean will be likely to be close to some value X. Okay, so that's a much more strong statement, and that's what we need to argue about replicability. Now, of course, here, likely to be close to X is rather loose formulation, but I will show you in a minute how we can make that much more formal. Okay, now, what type of statistics, or what statistics people typically use in order to synthesize their data? They collect a sample, and then very often you see in papers reporting the mean, and if you're lucky, the standard deviation that give you respectively information about the central tendency of your sample and the variability that you observe in the data, right? Because the mean is just one part of information. Okay, now, do you think that those statistics tell you anything about the expected performance? Think about it for a second. Well, usually when you have prompts like this with the question, the answer is typically no. But more interestingly, why? Why? Well, because the expected performance is a prediction, right? And as I just explained before, if you think that the mean and standard deviation of your sample are giving you something about the expected performance, you're making two mistakes. The first one is that the mean of the sample is not the same thing as the mean of the underlying distribution. This is what I was explaining just before. Okay. The second mistake is that the underlying distribution is not normal. Almost 100% of the cases, when you're doing experimental research on real system, you collect data, the data you collect is not normally distributed. And this is a problem because the mean and standard deviation are a lot used because people have this picture in mind. And they have the idea that if I report the mean and standard deviation, then roughly speaking, 68% of my sample gonna fall between the mean plus minus standard deviation. So that's kind of interesting. But the real life is not that. The real life is something like this. Well, this is an experiment that I actually conducted during my PhD. I was measuring the end-to-end latency between different packet transmission over some given system. And it's not normally distributed, right? You typically have a massive amount of data on one side and then a very long tail with outliers. Or you may have things that actually resemble a normal distribution, but are very, very, very unlikely to be. Now, I'm not saying that it never happens, but what I'm saying is that you should not assume that the data is normally distributed unless you have very, very good reason to know it is. And most likely you don't. So don't assume the data is normally distributed. So what should we do, right? I'm essentially telling you that you should not report the mean and standard deviation. So what should we do instead to address those two problems that I was saying? The first problem we said was the confusion between descriptive and predictive statistics. Predictions are uncertain, and to capture this uncertainty, we need to use something. One approach is to use what is known as confidence interval. And the second problem, which is about the non-normality, encourages them to use what is called nonparametric statistics. And I'm going to present those two things in a second. So first, confidence interval. What is that? It's extremely simple, actually. A confidence interval is a numerical interval in which lie the given value, for a parameter of interest within a certain probability that is known as the confidence level. So to give you an example, we have again our sample. And if we say that the interval AB is a 95% confidence interval for the median of the thing we're measuring, which is called X, then it means that the probability that the true median of the distribution of X lies within A and B with a probability which is at least as large as 95%. That's what a confidence interval is. Now, nonparametric statistics, it's quite simple, actually. It's a generic term that refers to statistical methods or approaches that do not make assumptions on the nature of the underlying distribution. So typically not assuming that the data you have comes from a normal distribution. You may or may not know a set of approaches that do make such assumptions, and they are others known as parametric, and they have equivalents in the non-parametric world. The difference between the two sets of approaches is that, well, the parametric methods tend to be more powerful, which means that with the same amount of data, you're able to make more precise estimates. But those estimates are only true and correct if the underlying assumptions hold, meaning the data comes from a normal distribution for those examples. But that's not the case. So because we cannot assume normality, we are bound to use non-parametric methods instead. And I'll get that in a second. I'll get to that in a second. So takeaways from that statistical part. First, in order to talk about replicability, we need to make predictions. Right? We need to be able to make predictions. Second, to make predictions, we need to quantify. When we make predictions, we need to quantify the uncertainty. And one way to do this is to use confidence intervals. Second, third takeaway, you need to use non-parametric methods because we are not able to assume that, or we should not assume that the data is normal in most cases in empirical research. So 3 things to remember. As you see, not that big of a deal. Now, are there any questions so far on the statistical part or in the introduction? I don't see anything in the chat. Any question by voice? Anyone? Can you define non-determinism in a system? Okay. So for example, I gave the example of a wireless communication link earlier. Sorry, I was reading another question. So yeah, if you take a wireless communication system, so a small embedded radio that sends a packet to another embedded radio, you have a certain probability that this transmission between the 2 nodes will succeed. And you can measure this with the signal to noise ratio, with some other metrics that gives you an indication of what you can expect, but it will always remain a stochastic process. You're not guaranteed that this will succeed. That's an example of non-determinism. Another example would be that in cache systems, right? If you don't want to embed the state of your cache into your model, then so you don't know whether what is the current data available in your cache, you don't know whether you're going to have a cache hit or a cache miss, and this will impact the response time of your system. That's another example of non-determinism. I can elaborate if this is not clear enough. There's another question. What are semi-parametric statistics? I do not know. That's not a term that I've ever seen before. If that's something I said, it was not intentional. I don't know. It might exist, but that's not something I know about. Are there other questions?
So I have one question.
Yes, please.
Yeah, you spoke about the confidence interval, right? So
yes.
How do you then fix the probability for the confidence interval?
We're going to get to that just in a second. So there are different ways of computing confidence intervals, and I'm going to show you one way of doing it just now, and with the definition of how we compute the probability for that interval.
Okay, thank you.
Any other questions? All right. So for those of you that ask questions in writing, please let me know whether this was clear or not. Otherwise, I will elaborate when we get to the break. So I talked already quite a bit about this notion of timescales and the basics of statistics we need. And all that we have combined together in this methodology that we call TriScale, which is essentially a framework that is based on this notion of this observation I presented earlier, that the variability is present in the data along 3 different timescales, which we call runs, series, and sequels, where sequels are repetitions of series. And the framework looks something like this, right? So we have our 3 timescales in columns, and then we have 2 pipelines. One pipeline is what we call the design pipeline, or the experiment design pipeline, where we find, again, the 4 questions I've introduced before. How long should my run be? How many runs should I need, etc. And the analysis pipeline, we realize that we have corresponding questions or corresponding tasks for each of the timescales. So for the timescale of run, what do we have to do in the data analysis when we need to synthesize our raw data into metrics? In the sequels, we have to synthesize the result, our metrics into KPIs and so on. And so in the end, how do you use the framework? Well, you input some definition about what you're interested in measuring, which metrics, KPI, and variability scores you want to use. At the end of that design pipeline, you get some information about indication about the minimal number of runs you should use in order to fulfill those expectations. You then collect the data, which is not part of the framework. You get the raw data, which you can push into your analysis pipeline, and then at the end of the analysis pipeline, you get some performance results, which, much more interestingly than what we saw before, can now are associated a level of confidence, meaning that we have some intuition about how confident we are that those results could be obtained again if we were to rerun the experiment. So how does that look? I'm going to dig into some parts of that framework. The first one is going to go back to your question. I think it was Aritra. How many runs do we need? So how do we answer such questions? In TriScale, we define KPIs as percentile for the distribution of our matrix value. So just one step back, remember, in the first time scale, we do our runs, we compute metrics. We do that several times, we get a set of matrix value, and then second time scale, we synthesize this. And we synthesize how? We try to synthesize by predicting the values of certain percentiles. So practically, and why do we make this choice? Well, we make this choice because there exists a method that was introduced by a mathematician called Thompson to compute confidence interval using a non-parametric approach for percentiles. So essentially, it fits the bill that we set ourselves before, right? We need non-parametric method. We need a way of establishing confidence interval. We can do that rather easily with percentiles. And here is how. Let's take, for now, let's say we do one measurement, right? We do one measurement of a value of our parameter X, and we get this value here. Now, think of, we are trying of predicting what is the median of the distribution of X, knowing that we have only one sample. What do you think is the probability of the median to be above or below that sample? Think about it for a second. Well, the probability is going to be 1/2. Why? But because of the definition of the median. But the median is what? Is the statistic. It's a numerical value that is computed in a way that it divides the distribution of parameter into two parts of equal probability. So if you get one sample, then this one sample has equal probability to be on the top part of the distribution or the bottom part of the distribution. And therefore, the median has 50% chance to be above or below that value. Okay? Now, if you take a second measurement, right? Take a second measurement and we assume that those two measurements are dependent from one another, then the probability multiply. And what happens is that now with two samples, the probability that the median is below both of them is 1/4. Why? Because well, it means if the median is lying in that interval, it means that both our measurement points fell into the upper part of the distribution. Each of those events have probability 1/2, they get multiplied, they have probability 1/4 altogether. Probability 1/2 in between, and probability again 1/4 above those two values, symmetry with the same sort of argument. And of course, if you do a third sample, you're going to have the same process, fourth sample, and so on and so forth. And actually, you can look at the numbers and then realize that the probability of any percentile P to lie between two successive samples in our set of measurements follow a well-known distribution, which is known as the binomial distribution. Whether you know it or not is not a problem. And then we can work on that equation, play a bit with the math, do some summation so that we can design or we can compute expressions for any sample xm to be a lower bound of any percentile P that we're interested in estimating. And this is essentially what we need in order to compute confidence interval. We now have a way of saying, I want to estimate a percentile P, the median, the 95th percentile, and then I can compute the right term, which gives me the probability for xm to be a bound for my estimate. And if I combine the bound, I get a confidence interval. I see a question from Mohammed. Can you give an example to understand more the approach? Can you clarify which approach you're talking about? Yeah, I'm going to carry on, let you write, and then I'll go back to this whenever I have more info in the chat. So bottom line, you can use this approach, which is due to, doesn't really have a name. It's only due to a mathematician called Thompson, to essentially estimate any percentile with any personal level of interest. The interesting bit is that you can flip those equations around and extract n, which in my equations were the number of samples. And where C is the confidence level, P is the percentile value. And that directly gives you the minimal number of runs you need, or the minimal number of samples you need to make any estimate you're interested in. So if we fix the confidence level to say 95%, which is quite standard in the field, in statistics, for the median, you plug the values in. For the median, you obtain that you need a minimum of 6 samples, which is okay. But if you increase the percentile value, then you're going to increase also, or you make the percentile value more extreme, then you increase the minimum number of runs you need, which is quite intuitive. For the quartile, so 25th percentile, it increases to 11. And if you go to 95th percentile or first percentile, it already jumps to 300, or almost 300. And if you go to 0.001, which correspond to this 5.9 reliability that you may have heard of as a requirement for predictability, then you get to an absurd number. So like essentially you need 300,000 samples in order to be able to make such estimates. Nobody is able to do that in almost any context that I know. More graphically, how things look like. So let's say we are still interested in computing 95% CI for the median. If we have 1 sample, we cannot say anything. 2 samples, 3 samples, 4, 5, 6. Number from before. 6 is the minimal number of samples we need in order to compute the first CI. And then the CI looks like how? Well, it's essentially the entire range of the data we have. And then let's say we keep aggregating more samples. 7 doesn't change. 8, 9. And when we get to 9, something interesting happens. Is that if you compute the probability with the math that I showed you just before, you can see that you can start excluding the most extreme samples, and the probability that the median lies between essentially all minus the most 2 extremes already exceeds 95%, and therefore x1 to x2 to x8 in this example is already a 95% CI. Of course, if you keep adding numbers, this process continues, right? And you're not guaranteed that the confidence interval will always get narrower with more data. Why? Because if you start getting more extreme points, that your confidence interval might shift, like it's the case for n equals 10. But essentially, that's the tendency, right? And it makes sense. The more sample you get, the more narrow your confidence interval will tend to get. So Mohammed asked, okay, so can you give more an example to understand more on the slide where we calculated the bound on the parameter x? I'm running slightly short on time, so I'm going to hold that question, and we can come back to this during the break. Because now I would like you to start. Well, we're going to do together the first short hands-on session. And for that, I will ask you to open a new browser window and go to triscale.ethz.ch, and you're going to end up on a page that looks somewhat like what you see on the slide right now. And I'm going to do that with you. So this is the page how it looks like now. And I have prepared everything you need in order to do this hands-on part. So the only thing you need to do is to click this launch binder button, part 1. And when you do this, you're going to see a page like this. I can explain what Binder is, it's essentially a way of making or running Jupyter Notebooks into a web browser. Just so that you can actually run the code and give it a try without having to install anything. But for that, what needs to happen, that's why we're waiting for now, is that the code is packaged into a container, which is being launched and served into some server, and then you get access to that so that you can interact with the code. So it takes about a few seconds, tens of seconds, so that the thing opens. So we just need to wait for a little bit. That should start soonish. There we go. And so, okay, so once the thing open, you're gonna get into a Jupyter Notebook. If you're extremely unfamiliar with Jupyter Notebooks, I've also prepared notebook basics that you can see here, notebook, to tell you how to use notebooks. You can have a look at that. There's no need that we do that together. You can have a look at that later on. You'll have a bit of time for that. So what are we looking at? We are looking at a Jupyter Notebook in which I present essentially how to use TriScale to implement the first pipeline that I presented, so this experiment pipeline, and in particular, how to answer that question of how many runs do we need. And everything is implemented for you. So all the maths that I just talked about has been implemented into a Python package. It's called TriScale, which we're going to load just right now by executing the cell. And essentially, the only thing you have to do is to get the information of how many runs you need is to define the percentile of interest, let's say the median, the confidence level you're interested in estimating. Then you run this experimental sizing function. And then you get what? You get the answer of how many samples are required for estimating that percentile at that confidence level. Of course, you can change the numbers, for example, 65%, and then you know that, okay, for the 75th percentile, then you need 11 samples. And you can increase that as I presented in the slide. Rerun the cell, and then you get to this about 300,000 samples that I showed before. Now, intuitively, it takes the same number of samples to estimate percentile that are symmetric from one another. Why? Because essentially all the probabilities are symmetric around the median. I guess it's quite intuitive. I can try to elaborate if it's not clear for any one of you. I'll take that into the question. And as I already showed you, in the next cell, we compute different values for a range of percentile and a range of confidence level. And if we can visualize this with some colors. What you can see is that on the y-axis, we have the confidence level from 70 to 100%. In the x-axis, we have the percentile. So you see again that this is symmetric, right? The left side of the figure looks the same as the right side. And interestingly, you see that it does not cost you too much to go from 70 to 100 in terms of confidence level. However, it does cost you quickly a lot more when the percentiles start to get more extreme, which is kind of an interesting observation I found. And the last thing I've showed you in the slide is that when we aggregate more samples, eventually we can start excluding the most extreme values. And so you may not be only interested into what is the minimal number of samples you need, but you may want to know, like, okay, how many samples do I need such that I can compute my confidence interval and I can exclude the worst, let's say 3 data points, because you may have some outliers in your experiments it's unavoidable in many fields. And you can also do that with the same API. You can do that with an optional argument, which is called robustness. It's not extremely well chosen, but for now, this is how it's called. They're essentially saying how many samples do you want to exclude, and you get a similar number of answers. So in this case, for example, with the 10th percentile, 95% confidence level, with 3 runs, the 3 most extreme data points being excluded, you need 97 samples, for example. So the values I pick here for confidence and percentile are arbitrary. And again, quite obviously, if you ask to exclude more and more samples, sorry, let me scroll down again a bit. If you exclude more and more samples, so you increase the robustness parameters, the number of runs you actually need increases, but you can see that the increase is pretty much linear. So it does not cost you too much if you want to exclude more samples, or it's quite predictable how much it's going to cost you in terms of minimal n, meaning on the number of runs you actually need to perform. All right. So now it's actually your turn to try to play a bit with this functions and this API. So it's pretty simple. I've put here, you're not going to see it, I guess. So let me do quickly this. There we go. So that I can keep scrolling down. Okay. So I've set for you a couple of questions. So what is the minimal number of runs for doing a for certain percentile and confidence values? And just give it a try, play a bit with the API, with the function, so to see how if you can get the right answers. If you're desperate for the answers, you can find the solution here. You only have to click, and then you will get the answers there. It's already 15. Well, it's 58. For me, it's 3:58. I hoped. Okay, let's say I give you 5 minutes to have a look at this, and then we'll do a break for 15 minutes, and we'll resume with the second part. The second part is going to be shorter, so it's not a big deal if we're slightly over time now. All right, I let you have a look at this. 5 minutes, so at 4:03 or whatever time zone you are, 03. I'm going to quickly comment on those results, and then I can take other questions in parallel. All right. So Mohammed, you said it's fine now, or do you still need more intuition about the computation of the bounds?
Sorry, you are mute now.
Oh, sorry about that. I muted myself at 2 places. That was not a good idea. Yes, so I got a couple of questions in the chat. I'm going to take them, but before I just want to finish quickly on the first hands-on part. So the questions were not meant to be hard, at least the first ones. So just to give you an intuition that essentially that's pretty easy for you to use, right? That's really the main message here. So the numbers don't really matter. What I want to show is that it's essentially pretty easy. If you trust the math, and I hope to convince you that it is trustworthy, then you can simply input the numbers for confidence interval you're interested in and percentile, and then you get an information, rational answers about how many runs at minimum you need to perform. Right? And I will explain in the second part of the presentation, how does that relate with the claims we can make. So the interesting observation is just to confirm something I already said, right, is that if we increase, so if we go from 90 to 95 for both the percentile and then for the confidence level, then what we observe is that it's actually increasing the percentile costs us more than to increase the confidence level. And that tends to be true pretty much for all numerical values. That's essentially what you can see here, right? And what I showed before. If you go up in confidence level, the number of runs does increase a bit, but it's much less extreme than if you go from 90 to 95 or 95 to 95.5 percentile. That's just the point I wanted to stress here. And you can play a bit with a bit of a loop to see, to play with the robustness parameter, but it's not really critical. All right. Any specific question on the hands-on part itself? I'll take that as a no. Now, so 2 questions. I'll take first the one from Aritra because it's going to be shorter to answer. So Aritra was asking, what is specific thing in this framework in TriScale about networking? That's a great question. Why do I love it? Because actually, it's more the other way around. The methods are not particularly specific to networking. And this is why I'm giving this talk and also in other communities, because a lot of the things that I've talked about, in particular, the things I've talked about in the first part, so in the first block, are quite widely applicable. But the framework has been designed for networking application in mind. And what is specific about that are the type or the nature of the variability that you see. And as we're going to discuss in the second part, how do you do to handle them? More concretely, one important factor for variability in networking experiments is time. It's the time of the day or the time of the year that the experiment runs. If you consider the internet, for example, or even wireless communication or cellular communication, you have more traffic during the day than during the night, right? Why? Because the traffic is mostly generated by human, and while humans are awake, sorry, let me remove that. Human will communicate when we're awake, so more communication during the day than during the night. Netflix traffic is mostly present at around 8 and 11 p.m. during the day. And this is what leads us to this strong emphasis on timescales. And in other areas, in other fields that are not specifically networking, you may benefit from a different emphasis that on time, and therefore you may think about a different design. At the end of this presentation, we're going to talk about a bit more about the specific challenges of ML, and you're going to see that if I were to do the same work for ML, I would not put the emphasis on the same things. All right. Now, question from Mohammed is clarification on how we compute the bounds. So let me go back to the slide here. So I'll take it back from here. I hope this is pretty much where the confusion was. If not the case, then please tell me again, and we can do that offline during the break. So what I was saying is that the intuition, you can see on that picture, the intuition is that the percentiles have by themselves an interesting definition, which is that they divide a distribution of values between known shares. Right? So if you take the median by design, it's the numerical values for which you have 50% of the data, so 50% of the distribution on one side and 50% on the other side. And so if you flip that around, if you take one sample, you do one measurement from your distribution, then this one measurement has 50% chance to be higher than the median or lower than the median, because that's the definition of the median. If you take, for example, the 25th percentile, and then you do, again, one measurement, then this one measurement has 75% to be above the 25th percentile and 25% chance to be below, because that's the definition of the 25th percentile. And assuming we can rely on independence, which we're going to talk about in the second part, then you can multiply the probabilities with multiple samples, and then you can use this intuition to compute the probability for percentile to lie in between different successive samples. So for example, here, if I have 3 between the first and the second, so the smallest one and the second smallest, then the probability of the median to be between those two, you can compute to be 3/8. And actually, the more general formulation is shown here. And then if you play a bit, you make sums over K, essentially, and then you can define upper bound and lower bound for any percentile. And this is what we use. This is essentially the Thompson method, and this is how we can derive confidence intervals for percentiles in a non-parametric way. So we make no assumption whatsoever about what the distribution looks like. And when we do this, and essentially the implementation of that just right here is what you've played in the notebook. It does no more, no less than that, at least in that part. Okay, so I hope that makes things slightly clearer. Otherwise, feel free to let me know. Now, it's 10 past. We're going to take a 15 minutes break. Let's make it 10 minutes, okay? Because we are slightly over time already, and I don't want to run over. So I had planned to resume at 1/4 past. Let's resume at 20 past, okay? So I'm going to edit that in a second. Let's resume at 20 past with the second part, where I'm going to talk about independence. I'm going to talk about ML finally, and a few more things. So enjoy the break, and I'll catch you in a little bit. Where is the break time? There we go. All right. So it's 20 past, so let's resume. I hope you had a good break. Some follow-up question from Mohammed. If you're interested, you can have a look in the chat. I've answered directly in writing there. Good. So in the first, oops, sorry about that. Let me bring myself back. There. Okay, there we go. So in the first block of the lecture was the longer part. As I said in the intro, second one will be slightly shorter, about 20 minutes or so, which leaves us time for further questions. And I will quickly show you some other hands-on. We won't take too much time because, well, we have only 2 hours. So in the first part, I have started to present you this TriScale framework. And in the last part of the first block, we started discussing this idea of how many runs do we need to perform in our experiments. And actually, I've showed you that the way to answer that question is by one way to answer that question, the one we use in TriScale, is to link this with the way we're going to synthesize the results, so the way we do the analysis. And in that time scale, this analysis is computing KPIs. So the two things are linked, and we're going to use a similar process for the other time scales, by the way. So meaning that we're going to link the design pipeline and the analysis pipeline. And this is how we manage to get what I call rational answers for the 4 questions we have up here. So in the second block, I will first, very briefly, you will see talk about how do we practically assess replicability. So how do we answer the question, like, are the results replicable? Or what is the confidence that they are? Then we need to talk a bit about independence. So this was implied in the first part of my talk, and we cannot do this in many cases. So that's really the elephant in the room here, and we cannot neglect that. And finally, I'll conclude with some thoughts on how ML is different from what I talked about in embedded systems and some specific challenges for replicability in machine learning. So first thing first, how can we assess replicability? So again, I showed you this slide before. Replicability is what? Is the intuition that if we use the same analysis, but we collect new data, so top right, we get essentially the same results. But what does that mean? What does same result mean? Right? The problem is that in the many statistical approaches that exist are extremely powerful. They are designed essentially to highlight when things are different. So to say that sample A is larger than sample B. But to say that things are the same, essentially all the approaches that you found, or that I found in the literature, was that they all boil down to checking whether the differences between 2 samples are pretty much bigger or lower than some threshold. And the problem is you need to set that threshold somehow. And we were interested into finding like a methodology that could be applied in different contexts for different systems and so on, and how to set one threshold to test them all. It didn't feel like it was any good way of doing that. And so instead, what we propose in TriScale is that we should actually not assess the replicability as a binary criterion of yes, no, this is replicable, this is not. But rather what we should do, and that we propose to do, is to quantify the amount of variability. Right, so it's kind of dependent. So we are not saying like yes or no, those results of this experiment are replicable, but instead we are trying to quantify how much variability we have. And then on a context-specific case by case, we can argue whether we found this is too much or this is still reasonable. And so, as you might already have guessed from the first part of the presentation, the way we do this is by computing what we call those variability scores, right? Because we're trying to quantify variability. And this is what the third time scale gives us. Why does it happen at the third time scale? Because essentially what we were saying is that I do one set of experiment one day, I do another set of experiment next month, and again the month after, for example, and then I look how much variability I have in between them. And this is likely to be representative of what variability someone else would find if they were to do your experiment again at a normal point in time in the future. So that seemed like a fairly good approach to quantify variability. At least that's the one we propose. And the good news is that you know already how to do this. Why? Because we use the exact same method as for the KPI. But we use again this Thompson method to compute again confidence interval on the percentiles. So what happens is that now we've defined percentiles. We have defined KPIs as percentile of the metric distribution, and now the variability score we define as percentile ranges for the KPI values. So this is what is illustrated on the right here. You see on the plots the different KPIs, right? And we measure confidence intervals based on those KPIs so that we estimate how much those KPIs vary over time. So the math is exactly the same. We use the same method. I'm not going to cover it again. You've already seen it. You can, there are more details in the paper and in the notebook I'm going to show you in a minute about why and how this works. I'm going to skip that. But essentially, the key idea is that with this approach, we compute a confidence interval. The range of that confidence interval gives us the score. And then, as I said, on a case-by-case basis, we can assess if we want a binary criterion of replicable yes, no. Then we suggest to base it on the value of that score. And so looping back, this is how we compute the variability score. And based on the definition of that score, that gives us how many sequels we need to perform. So how many set of repetitions of our set of experiments we need to perform to be able to compute that confidence interval. That might be slightly confusing at the moment. I realize that. That's not a huge deal. The key insight here is that replicability should not be considered as a binary criterion. I strongly believe that this is bound to fail or can only work in a very specific context, like you're evaluating low power communication protocol on one specific testbed, for example. Now, at this point, it's high time that we talk a bit about independence. So what is independence? I said it's the elephant in the room. It's the thing that is somewhat here, but nobody's seeing it, or we all pretend that we don't see it, but we actually need that. And I've already done this before in the first part of the presentation when I was showing the Thompson intuition. I've said that we need to make the assumption that the samples are IID. What does that mean? I'm sure you've all seen this before, but you might not be very clear about what it practically means. So IID, first thing first, is the acronym for independent and identically distributed. Let's parse this for a bit. Independent means essentially memoryless. It means that the future samples are not correlated with the past one, meaning that knowing the past samples does not give you anything about what the future samples are likely to be. And identically distributed means that all samples are assumed to come from the same underlying distribution. I'm going to illustrate that in a second. So let's say we have this distribution, right? And again, we typically don't know it, right? So this is unknown. This is why we take samples of it to try to estimate it. We can take sample of that distribution, and as long as the distribution doesn't change, then the samples are identically distributed. Now, if the distribution does change, and then we keep taking samples, then the sample we get is not identically distributed anymore, but it becomes biased. It's biased because the distribution has shifted. And because we don't know the distribution, we don't know there has been a shift. Okay? Now, the independence, so the memoryless aspect is something that can be seen on what is known as an autocorrelation plot. So here is, for example, a time series of some data points where we can see some fluctuation with some average value that seems to be more or less constant. And actually, if you plot an autocorrelation, the autocorrelation is essentially how similar are data points in a time series or in a set of samples with one another at different spacing. Let me try to clarify that a bit. On the plot on the right, on the x-axis, you have what is called the lag, which is the time interval between, or the interval between the number of samples. So for a lag of 10, for example, what you do is that you compare how similar is x0 with x10, then x1 with x11, x2 with x12, and so on and so forth. So a sliding window of samples like this, with a separation of 10. And then you add up the similarity, and that gives you an autocorrelation factor at lag 10. You do the same thing for all the lags, and you get an autocorrelation plot, which is shown on the right. And on this autocorrelation plot, when you see peaks, as we have here, so you can see peaks, for example, at around, what is it, around 10 or so. So the first peak is always very big because it's at lag 0. So you correlate the sample with themselves, which is always 1. And then you look at the first peak, the first main peak, which is around 10. It indicates what? It indicates that in your data, in your time series, which is here, you have a strong correlation between samples that are 10 apart. That is essentially showing you that your data is not independent. This is one way you can empirically cheat that, verify the independence. Now, one thing to realize is that you will often hear or read people talking about independence, only independence. But actually, in many cases, when we say independence, we tend to mean IID. So we mean independent and identically distributed. That's a misconception that is often lead to a problem. And as I said, if you do not have independence, then what happens? Then you have correlation in your samples. And then the problem is that if you have correlation in your samples, then the sample appears to contain more information than it actually has, which means that if you see an effect which is very strong, for example, you have a flat line, no, this direction, you have a flat line that's strongly increased in one go. This is kind of weird if your sample are supposed to be independent. Like all the values are the same, and then all of a sudden all the values jump and start being much bigger. And that can be a fake effect due to, for example, distribution shift. This is not what you're interested in measuring a priori. Now, another misconception is that the independence or the IID-ness is a property of the design and not a property of the data. And again, we sometimes a bit too often make an abuse of speaking when we say that the data is IID, or the data are IID, depending on where, anyway. This is actually not a mathematically correct statement, because what we mean when we write or say data is IID, what we have in mind is that data has been collected from an experiment that was IID. Okay. But what does that mean? Concretely, it means that an experiment is IID if all the factors of the experiment have been selected in an IID way, meaning memoryless and from a static distribution. What is a factor? A factor is essentially anything that has an effect on the results of the experiment. In networking context, as I already said today, it's the time of the day is typically a factor, an important factor. Netflix traffic in the evening, day and night traffic are different, and so on and so forth. And so to get an IID experiment, you need to make a list of your factors and select them in an IID way, so memoryless, and using the exact same random procedure, meaning that they are the parameters you pick come from a static distribution, identically distributed. The problem is that this is extremely hard to do and impossible in many cases. And there are multiple reasons for this. Sometimes the factors are just beyond your control. When you're doing a wireless experiment, unless you put yourself in a Faraday cage where you can shield yourself from external environment, whatever is happening here and now, Bluetooth connectivity, LoRa messages going over, and so on, is beyond your control, and you cannot control that. So how do you guarantee that the RF noise around you is picked randomly? Another problem you may have is that the randomization can sometimes might not be done perfectly. So if you say that time is a factor, you should randomly pick the start time of your experiment during, say, 1 day. But since your experiment takes time, say an hour, then you cannot, once you've picked one, say you run at noon, then the time span from noon to 1 p.m. is busy. So you cannot schedule anything there anymore. So if you, and therefore you lose the memory less aspect, and you are not able to pick the second experiment time completely independently of the first choice because, well, it's busy from 12 to 1, and you cannot do anything about that. And finally, it's sometimes extremely hard to actually know which factors are significant. One of my favorite work from the embedded system work a couple of years back was showing that there was a strong effect of temperature on embedded components. This is, of course, no news. We all know that. But what they did not realize is that they were deploying their sensors and networking systems in some building, and they had some very strange behavior at a specific point in time that they found out was actually correlated with sunshine showing on some specific boards, which was essentially making the crystal drift like crazy because of temperature. And everything broke apart, and that had nothing to do with the RF, that had nothing to do with the code, that had nothing to do with anything else. It's pretty hard to, so they could spot that one, but how do you know that you don't have like less extreme factors that are impairing your experiment? All that to say that guaranteeing that your experiment is IID can be done in some field, but the chances are pretty high if you're doing empirical research in embedded systems that you may not be able to guarantee that they are. The good news is that, and one practice to remedy this problem is to try to test a posteriori whether your data appears to come from an IID experiment. So I spent the last 5 minutes trying to tell you that IID is not about the data, it's about the experiment, but that actually we cannot guarantee the experiment. So we are back with the data, right? So we look at the data and we say, okay, do I have an amount of correlation in my data that is sufficiently low so that I can assume reasonably that the experiment was set in a more or less IID fashion. Without getting into the details, this works in the following way. Such empirical IID tests look whether the data shows trend. And so to be IID, you should have no trend in the data. So the average should be more or less constant. And you should have no correlation structure, meaning you should see no significant peak in your autocorrelation plot, roughly speaking. This can be done, but there are two important caveats to note. And so as I show on the right, this is implemented in TriScale. So you can actually use the tool in order to do those tests on the data you actually collect. But you need to keep in mind that this is very imprecise. I mean, not very imprecise, but it's not a perfect method. In particular, when you have a few samples. And so if you're constrained, if you have constraint in your experiment that you cannot have more than 10 or 15 samples, for example, then you need to keep in mind with such low numbers, those empirical tests are fairly fragile. And another issue, so the last point on that note is that it does not guarantee you anything about the future, right? And things may change. And again, this is a specificity about networking, which I'm going to skip for today, which is known as seasonality. Seasonality means what? It means that you may have recurring patterns in your data, typically days and night. Right? It means that if you don't pay attention about the time of the day, then you may reach wrong conclusions if your test, you have one set of experiment during the day and one set of experiment during the night, nighttime is more favorable for networking because there are less cross traffic, less interference. And so you need to take that into account. And you will not see correlation in your data if you only have daytime, because during the day, it feels okay, but it doesn't tell you anything that things won't change in the future. I realize my explanations are not extremely clear, but it's not a huge point. So I'm going to slide on that and move on with the last part, which I expect, given that you attended this lecture series from ESWEEK on embedded learning, you might be more interested in, which is a few thoughts on the replicability challenges in machine learning. Now, again, I want to stress that I do know machine learning. I work with it a bit, but I definitely don't qualify myself an expert. So take everything I say as my personal opinion and with a grain of salt. I've showed this slide already a couple of times. Replicability is with different data, same analysis, we obtain the same results. How do we translate that into a machine learning context? So the same analysis, that's pretty easy, right? So for ML, same analysis, for me, we are using the same machine learning model, right? We do the same sort of inference somehow. But the different data is not so clear, at least not to me, right? It could mean different things. It could mean that we are using different training set, or we are using a different test set, or you're using a different set of hyperparameters. All that is somehow different data that has an impact on our results, right? And it's not so clear what we should focus on. And I don't think it's actually a good idea to give a strict answer to that question, because it might depend on the context. Essentially go back to what sort of claim you're trying to make. So of course, there are a lot of choices you make during training that have a huge impact on the overall performance of your ML system or your model. The data you actually use for training, if you have a huge set, you need to sample, you cannot train with everything. Or the other way around, if you have very few data, the way you augment it to train also has an impact. The way you initialize your weight in a neural network, the hyperparameters, and so on and so forth. I'm sure if you know about machine learning, you can come up with more examples of that. All that to say that it's not just about the data, it's also about the design choices you make in your experiment. So it makes the decision or the boundary between analysis and data a bit more blurry somehow than in the networking world that I talked about before. And another thing is, to me, it's not so clear what we mean when we say what's best performance in a machine learning context. I've showed you this example of banana and kiwi at the very beginning, right? And we were saying we are interested in looking at energy consumption. And then we can say, okay, energy consumption, we have one metric, it's pretty clear. We test, and for this one experiment, A is better than B, I get a lower energy consumption. Fair enough. But in a machine learning context, is to me not as clear. Of course, you can do measure metrics like accuracy or F1 score or things like this, and then you can get something similar. But there's actually more to it, right? Like there's this definition of expression power or prediction power of different models. If you compare, for example, a random forest to a neural network for a classification task, I mean, of course, you can measure their output performance, but there are things that a neural network can do that a random forest will never be able to do. And whether that's something you're actually interested in doing, in measuring or not, is subjective. So maybe a model being better, say, if I want to say that neural networks are better than random forests, it would mean I could make that statement if I'm interested in the power of expression of the models. But I could be interested in simpler things, like if I tune better my model, I can achieve a better F1 score, and that's what I want. Or you could come up with other definition of best. And I think there's no right or wrong. It's kind of a subjective choice. Sorry for the typo, by the way. And essentially, they are all good, or they can be several good answers, because in my opinion, they measure different things. And it's not clear a priori to me what would make more sense to pick. It really depends what you're trying to evaluate. Now, in machine learning, one way to address the replicability problem is to have strictly defined benchmarks. And here are just a couple of examples that I know about. You may know more or different ones. It's fairly easy to do because of the nature of ML, right? You can define a very specific task, a very specific training procedure, a very specific testing procedure, and then everybody runs on the same thing. You can even bound, for example, the hardware you're going to train on. You can bound the time allowed to train, and so on and so forth. Doing something comparable in embedded system is not so easy, right? And I've already showed you why, right? It's not so easy because the experimental environment in which we test embedded systems is the physical world, and it cannot always be exactly replicated. That's precisely why we've started to work on TriScale. This is why TriScale exists. TriScale exists to try to foster the replicability of the experiment so that we can eventually compare them and benchmark. Right. By the way, I've started to work on that project on TriScale and this notion of fostering replicability precisely because we were trying to set a benchmark for IoT, and we realized we were not able to replicate our own results. So we are not quite ready to benchmark. So if you're not able to set strictly defined benchmarks, like in embedded systems, or if it's more challenging, another approach is to do essentially, again, try to design independent or IID experiments. And for that, well, then you need to randomize all the factors that you're not specifically interested in setting in stone. So that's exactly the same approach as we use in TriScale. Right? But what we said is that for networking, essentially pretty much everything boils down to the time at which you do your experiments. It's oversimplified, but it can be seen like this. So that's time is what you need to randomize. If in the ML context, you could do something similar. So you could say, I want to randomize any of the choices I make in my training, for example, and then I run my experiment for different values of those trainings. The problem is the computational cost that has. Like if you've been working with advanced machine learning model, training costs, as you know, more probably better than me, training costs, access to testing data, and so on, are significant. And when I say cost, it's not only financial cost, but also just time cost, the time it takes to actually retrain, retest the models. So that can be an issue, right? That can be a different type of issue, more specific to ML, where you cannot just do 100 times 100 repetition of your training just for the sake of randomizing your parameters. Maybe you can, maybe you should, but it's not given that anyone can. If you're interested in this question on replicability in machine learning context, there are two very recent references that I particularly like. There's one from the MLSys conference from this year, which specifically look at the benchmarks that exist in machine learning and argue that we should account for the variability in those benchmark results more in the evaluation or in the ranking of the different solutions. So saying which approach is best. I really recommend this paper, is really nice. And another, it's not really a paper, although you will find a paper there. It's generally a research project from Princeton, where they essentially set up to look at papers from the literature in different fields that use machine learning and try to replicate the results. And it often fails, spoiler alert. But what they were interested in is trying to understand why it fails. So what were the mistakes made by people in their use of machine learning that made the results irreproducible? It's also very interesting because it gives I found quite a lot of insight into the misconception that people have about using machine learning, because as you know, as well as me, as that a lot of people are using machine learning in your research. You may be doing it. I've been doing it without being a machine learning expert myself. So when I do this, I'm very likely to make some fundamental mistakes because my understanding of the tool, which is machine learning in general, might not be so deep. And so that project is really about like trying to understand what people do wrong, which I find extremely interesting. All right, so that concludes the few thoughts I had on the machine learning aspects. I want just to quickly show you something I've called a mini hands-on session, which is a bit of a misleading title, because you will not actually do anything, but you can if you want in your own time. That's why it's still hands-on. So for the second timeline, the second pipeline in TriScale. So earlier we looked at the experimental design, and similarly in the TriScale tool, you have a number of API functions, or you have a number of functions in the API that facilitate the computation of metrics, KPI, and variability scores. And that you will find again linked on the website. So if I open again this, there we go. So again, on the website, if you click on part 2, it will open a new binder. I should have kept this one open, actually. Does this work? Let me see. No, it doesn't. Anyway, so it was fast loading. So that's the second. If you click on part 2, you will eventually get to this notebook, which is about, as I said, data analysis. And I just want to show you quickly. There are some explanation about the API. So one function per time scale, and some examples of how to use them. And in addition to just computing the metric, you get some additional information, such as data visualization and results of the statistical test. In particular, so that's some random data that I've been generating, and based on that, you can compute the empirical IID tests. That's directly built in somehow. And so here you see, based on the data, we look whether we have trends or not. And then we can do the autocorrelation plot. And then you can see that although at like whatever 48, we seem to have some correlation that might be stronger than if the experiment was truly IID, but we don't have any strong peak like we had before in the presentation. And so TriScale compute those things, provide you with the information, and then you need to use your expertise and critical thinking whether to assess whether there is something fishy in your experiment and there are correlations that should not be there, and then you need to go and look what's going on, or if everything looks to be kind of okay. And in this case, everything looks to be kind of okay. We don't have strong peaks, which actually makes sense because the data, if you look at it, has been generated just from a random sample. So there's practically no correlation because it's designed like that. Yes, and then there are some more example, a use case to let you play around with some actual data that was collecting part of the research project. I'll let you have a look, and if you have any questions, feel free to reach out and we can discuss that. All right, so let me go back to the slide for a quick wrap up. I'm slightly running out of time, so if there are any questions, I will take them at the end. I just want to do a quick summary of today's lecture. I kicked myself out again. Okay, there we go. So quick wrap up. In the first block, I first motivated why replicability matters. I showed you a concrete example where it's not really clear from the results whether we can expect some presented results in papers, whether they would be replicable or not, or we would feel confident that we could obtain the same results. I've showed you, I presented this intuition that maybe it does not matter so much where the variability comes from, but it's more interesting to look how the variability looks like, then try to address the shape of the variability rather than the source of it. And then I try to give you like the basic the basic knowledge, few bits of knowledge that you need to know about statistics in order to be able to reason about replicability. And then the second block, we talked about this idea that assessing replicability as a binary criterion seems quite tricky, or it's difficult to do in a general setting. And so instead, we rather, in the TriScale approach, we suggest to quantify it instead. So measure how much variability you have, and then use that as a measure for replicability. I try to explain this notion of independence, what IIDness means, why is this important, and one mean to check empirically whether your data appears to be IID or not. And this is extremely important because if it is not, then all the computation you do about the confidence interval and so on don't hold anymore. And finally, given the theme of this lecture series, I've concluded with some thought about replicability challenges in machine learning, why is it different from ML, and what can be done about it. So in this figure about TriScale, those are the blocks I covered. There are a few other things that I did not cover today. Notion of how long should the run be, and there's some things to be discussed about convergence. I've hinted some issues about seasonality in the data, and then more generally distribution shifts. Those are things that are also covered by TriScale, even though I did not present them today. There's also some interesting discussion to be had on how do you compare confidence intervals, but it actually goes even beyond the scope of TriScale. But if you are interested in finding more info about this, on the website you've already visited, triscale.ethset.ch, you will find a link to the paper with much more information about all those points in there. With that, I would like to conclude this lecture. We have set up a small survey, and which I would like to ask participants to fill out if you have a minute. Feedback for us to get an idea about what you like and dislike about this presentation, and suggestion to make it even better in the future. So again, you will find the link pretty easily on the website. It's just up here. Like feedback tutorial. So please, after the session it's very short, take 3 minutes to give us some idea about what you liked or didn't like about it. All right, and so with that, I finally reach the end of this lecture. I hope you enjoy and that you've learned a few interesting things about what to pay attention to when designing and analyzing the data from your experiment. And if you have any further questions or comments or thoughts today or in the future, my contacts are easy to find. Feel free to reach out at any point in time. And with that, I thank you for participating today. And if there are any remaining questions, I'll be happy to take them now. Thank you, guys and girls.